Good afternoon, everyone. Let us start.
Good afternoon, sir.
Today, remember, we have been learning Chapter 9, Solar Radiation, Heat Balance, and Temperature. Today, we shall discuss about distribution of temperature on the Earth's surface. Now, let me present my screen. Distribution of temperature on the Earth's surface. So let us read. The global distribution of temperature can well be understood by studying the temperature distribution in January and July. So since we are in the northern hemisphere, here January represents winter season and July represents summer season. So temperature distribution is generally shown on the map with the help of isotherms. Okay, so what are isotherms? You might have learned earlier. Isotherms are lines joining places having equal temperature. Okay, this is an imaginary line joining places having equal temperature. Figure number 9.4a and b show the distribution of surface and air temperature in the month of January and July. Okay, see here these lines. Okay, so these lines are known as isotherms. Okay, so let us continue. In general, the effect of latitude on temperature is well pronounced on the map, as isotherms are generally parallel to the latitude. See, when we see, say for example, this is the temperature distribution in the month of January, that is winter season in the northern hemisphere. When we see this map, we find that these isotherms, okay, these isotherms are parallel, roughly, okay, almost parallel with the these latitudes. So these are the values of latitudes. Okay, this is the equator, and the deviation from this general trend is more pronounced in January than in July. That is, a deviation of these isotherms from the latitude is more pronounced, okay, in January than July, especially in northern hemisphere. See, if you see this map, say you will find that here isotherms are more banded. Okay, see here it is bending, more bending. These isotherms are bending is mainly in the northern hemisphere. Okay, that also on the continents. Why it is so? Let us see. In the northern hemisphere, the land surface area is much larger than in the southern hemisphere. Okay, see here, if you see here, we have this is the equator. Okay, this is the equator, and when we compare the northern hemisphere, so this is the northern hemisphere, and here this is the southern hemisphere. When we compare, okay, the land area, then we find more land. See here we have North America, we have Greenland, we have Northern Africa, and we have Europe and Asia here. So we find more land area as compared, okay, in the northern hemisphere as compared to the southern hemisphere. That is the point mentioned here. Okay, see, in the northern hemisphere, the land surface area is much larger than the southern hemisphere, and hence the effects of land mass and the ocean currents are well pronounced. Since the area of land in the northern hemisphere is much larger. The effect of landmass and ocean current is more pronounced in the northern hemisphere. Okay, so in January, the isotherms deviate to the north over the oceans, over the continent. Okay, in the month of January, what happened in the northern hemisphere? Okay, isotherms deviate in the north over the oceans and to the south in the continent. Just see here, this is the map. Okay, and here this is the map, and see here isotherms are deviated more over the ocean. Okay, this is Atlantic Ocean. See, it is bending towards the north, where it is bended. Okay, it is bending towards the south over the continent. Just see here. Okay, it is bending this way. It is bending towards the north over the oceans here, and towards the south over the continents. And this can be seen. So the reason is here. Okay, the reason is here. Say why it is bending. Why it is bending? Say towards the north in the over the ocean and towards the south over the continents is given here. This can be seen on the North Atlantic Ocean, and here the presence of warm ocean currents, that is Gulf Stream and the North Atlantic Drift, make the northern Atlantic Ocean warmer, and the isotherms, okay, bend towards the north. See here what is happening over the Atlantic Ocean. See here, this is the North Atlantic Ocean, and here we have this warm Gulf Stream. Okay, and this is the North Atlantic Drift. So this Gulf Stream and the North Atlantic Drift transfer heat from the equator. From this area, heat is transferred towards the pole, and that is why the isotherms are bending in this way. Okay, isotherms are bending in this way because heat is transferred from the equator towards the pole by the Gulf Stream and the North Atlantic Drift. Okay, so that is the point mentioned here. And over the land, temperature decreases sharply, and isotherms bend towards the south in Europe. Okay, and see, for the over the Atlantic Ocean, you have seen that these isotherms are bending, okay, towards the pole in this way. But here over Europe, here it is bending towards the south because temperature is decreases sharply over the continents. Okay, so that is the main reason why isotherms are bending towards the south over the continents. Okay, temperature decreases sharply and isotherms bend towards the south in Europe. And here it is, okay, this bending, it is most pronounced in the Siberian plain. Here the bending is most pronounced, okay, over the Siberian plain. Siberian plain is here. This is the Siberian plain. Okay, so here this isotherm of minus 25 is bending very sharply towards the south. The mean January temperature along the 60° east longitude is minus 20° both at 80° north and 50° north latitudes. Okay, mean January temperature along 60° east longitude is minus 20° Celsius both at 80° north and 50°. Okay, along this 60°. See here. Here this is 0, this is 30, this is 60, and this is 90. Okay, this is 90, and IT is somewhere here. IT is. Okay, here 30 east, then 60 east, and this is 90 east, and IT east is somewhere here. And so this is 30 north, then 60 north. Okay, and as mentioned here temperature is minus 20. Okay, minus 20 between 50 to say between 50 to this IT somewhere here. Okay, 30 here, this is 60, 50 is somewhere here, and IT is somewhere here. So between these two latitudes, okay, the temperature here is around minus 20 or 25 degrees Celsius. Okay, and the mean monthly temperature for January is over 27 degrees Celsius, and in equator ocean, and over these 20 degrees Celsius in the tropics, and 2 degrees Celsius to 0 degrees Celsius in the middle latitude, and minus 18 degrees Celsius and minus 48 in the Eurasian continental interior. Okay, see over the warm tropical oceans. Okay, here in January, see here in this area. Okay, here it is in this area, it is more than 20 degrees Celsius. Okay, and see this is 20 and 10 is here, and 0 is here. This is in the tropics. That is the point mentioned here. Okay, any question from your side?
No, sir.
Okay, then let us proceed. Let us read about July. So in July, actually you must know that since we are in the northern hemisphere, July falls in the summer season. So in July, the isotherms generally run parallel to the latitude. Okay, and the equatorial oceans record warmer temperature more than 27 degrees Celsius, and over the lane more than 30 degrees Celsius is noticed over the subtropical continental region of Asia. So this is the map for the month of July, and see here here the isotherms here are almost parallel with the latitude. Okay, so these are the latitude, let us say almost parallel, and here over the warm tropical oceans. Okay, here see you will find 30 degrees Celsius over the Indian Ocean, and here also 30 degree. Okay, and here also 30 degree, and over the North Atlantic Ocean we have these isotherms of 20 degrees Celsius. That means, so here we can say that the temperature is between 30 to 20, that is 27, around 27 degrees Celsius. Okay, over the tropical seas. And along the 40 degree north runs the isotherm of 10 degrees Celsius, and along the 40 degree south temperature is 10 degree Celsius. Okay, so along 40 degree north, let's see here, as I told you, this is 0 degree equator, this is 30, and here 40 is somewhere here, this is 60. Okay, this is 60, and here along this 40 degree north, here temperature is around this 10 degrees Celsius. Likewise in the southern hemisphere also, this is 30 degrees south, and let us say this is 40 degrees south, and here also temperature is around 10 degree Celsius. Just see here, just this is the isotherm, and it is almost parallel with the latitude also. Okay, so in this way you can examine these maps very carefully. Okay, and here this is the isotherm of 10 degrees Celsius and this is the isotherm of 20. Okay, and likewise we have the isotherm of this 20, say along 30 degrees south, and along 40 we have this isotherm of 10 degree Celsius. Okay, so this is about this July, that is for summer. Okay, distribution of temperature in the month of July. And see, we have one more figure. This is 9.5. 9.5 is here. Okay, so 9.5, this map shows the range of temperature between January and July. Range of temperature means difference between the maximum temperature and the minimum temperature. Here this range is between January and July. So what is the difference in temperature between July and January is given in this map. Okay, in this map. And so this is the map showing for the month of this July. So let us read. Here the highest range of temperature. Okay, the highest range of temperature is more than 60 degree Celsius over the this, or more, is more than 60 degrees Celsius over the northeastern part of the Eurasian continent. So the range of temperature is the highest over the this Eurasian northeastern part of Eurasian continent. Eurasian means Russia. So difference between January and July temperature is the highest over northeastern part of the sea here. This area, okay, this area, here it is. So this area, this is the northeastern part of this Eurasia, that is Russia. Here you will be seeing that we have isotherm of we have this range of 60 degree. That is the difference between the summer temperature, okay, and winter temperature is 60 degree. Okay, so the difference between temperature conditions in January and July is 60 degree over northeastern Eurasia. Okay, remember this is northeastern Eurasia, that is Siberia. Okay, here we have this one place called Barkoyansk, recording the lowest temperature over the earth. Okay, this is northeast the Siberia. And this is due to continentality. About the concept of continentality, we have learned in the previous lesson. Okay, when we discuss about the factors affecting the this distribution of temperature, or controlling factors controlling the temperature distribution over the earth's surface, in that we have learned about continentality. So what do you mean by continentality? Actually, this is the location of a place, okay, situation of a place very far away from the ocean. See here, here this area or this area is very far away from the ocean, and hence the influence of the moderating influence of the ocean is not available, and that is what we call continentality. Such type of situation is known as continentality. Okay, as you will find in that map also here. So here this area, okay, this area records. Here we find, in this area we find maximum difference between the winter and the summer because of this continentality. That means the influence of the ocean is not available in this area. Okay, that is what we call continentality. As I told you last time, say this is a big continent, and in the middle of a continent, if a place is located, the moderating influence of the sea is not available, and because of that, winter will be extremely cold, and summer will be sometime in the other cases will be hot. So such type of climate is known as extreme type of climate, and the situation is known as continentality. And here in the Siberian area, we find maximum difference between the summer and the winter temperature because of continentality. And the least range of temperature is that is 3 degrees Celsius is found between 20 degrees south and 15 degrees north. Okay, between 20 and 15 degrees north we find the least. Okay, see here, between here we have this 30 and 15 is somewhere here. Okay, 15 is somewhere here, and here we have 30 and 20 is here. So between this 15 degree north and 20 degree south, okay, between 50 degree north and 20 degree south, the least variation in temperature here is found. See here, 3 degrees Celsius here, 3 degrees Celsius. So this isotherm is 3 degrees Celsius, and this is also 3 degrees Celsius. So this is between what? Between this 15 degree north, okay, and this 20 degrees south. 20 degrees south. So between 15 degree north and 20 degrees south, we find the least variation in temperature, that is 3 degrees Celsius. Okay, up to here, any question from your side?
No, sir.
Okay, if you don't have, then next important topic is inversion of temperature. Let us read. Normally, temperature decreases with increase in elevation. This we have learned earlier. When we climb up a mountain, then temperature is decreased. Okay, temperature decreases with increased elevation, and that is what we call normal lapse rate. So what is the rate of decrease here? 1 degree Celsius for every 165 meters of ascent. So if you climb up 165 meter, temperature will be decreased by 1 degree Celsius, and this rate is known as normal lapse rate. But sometimes, okay, at times the situation is reversed. Instead of decreasing temperature with increasing height, you may find increase in temperature with increase in height. That is, the normal lapse rate is inverted, and this is called inversion of temperature. Okay, just let us see one diagram. See here, in this case, and here temperature increases towards this side, and this side represents height. Okay, height increases towards this side, and 0 is here. So this graph shows up to here shows normal lapse rate. That is, you will find temperature decreases with increasing height up to here, and again from this particular point you will find that temperature increases with increasing height. See here, as I told you, this temperature increases toward this side. Okay, so here from this particular point temperature increases with increasing height up to here. So this layer is known as inversion layer, as indicated here, and beyond this layer again we find this temperature decreases with increasing height. So this is the condition of normal lapse rate. This is also normal lapse rate, and this is the inversion layer. That is, there is increase in temperature with increasing altitude. Okay, so this is what I call inversion of temperature. And inversion is usually short duration but quite common. Okay, and say a long winter night with clear skies and still air is ideal situation for inversion, and the heat of the day is radiated off during the night and by the early morning hours. Okay, the earth is cooler than the air above. Just here we have one more diagram here. Just see here, sometimes you will find this cool air here. Say during the night time, the heat from the slope of the mountain is radiated very quickly, and you must know that once it is radiated, the air nearby it will be cooled down, and cold air is heavy, and that is why under the influence of gravity, cold air will be gliding downwards. Cold air will be sliding downwards and will be accumulated here. That means you will find cool air near the surface and warm air above it. See, the temperature near the surface is 4 degrees Celsius. Above it we have air temperature. We have air having temperature 8 degree, 10 degree, and so on. So in this way, inversion of temperature is occurred. So over the polar area, temperature inversion is normal throughout the year, and see here, surface inversion promotes stability in the lower layers of the atmosphere, and the smoke and the dust particles get collected beneath the inversion layer and spread horizontally to fill the lower strata of the atmosphere. Just see here, we have one photograph. Just see here. See here, smoke is rising from the factory, and it is spreading in horizontally. See here, it is spreading here in this way. So this is because of temperature inversion. So why the smoke is spreading in a layer? So this is because of inversion of temperature, and this is the inversion layer. And I have told you that when there is an inversion layer, it acts as a lid of a container, and the dust particles and others cannot go beyond this. It will remain confined in this inversion layer, and hence the atmosphere becomes stable. So that is the point mentioned in the textbook. So you must know that this is an example of temperature inversion. See, when you see say smoke rising vertically for some height, and if you have observed that smoke is spreading in a layer, in a thin layer in this way, it implies that there is an inversion layer. You may be observing later on also. And so another one, dense fog in the mornings are common occurrences, especially during the winter season. So when we see fog and a mist in the say during the winter season, in the morning, so that is also an example of this temperature inversion. But you must know that this inversion commonly lasts for a few hours, and until the sun comes up and being warm up the earth surface. And as I told you, inversion also takes place in the hills and in the mountain due to air drainage. Cold air at the hills and the mountain produced during night flows under the influence of gravity, as I explained you earlier. And this cold air, being heavy and dense, moves down the slope and then accumulated in pockets in the valley bottom, and this is what we call air drainage. As I explained you earlier. So in this case here, this is called air drainage. Cold air is gliding downwards, and it is accumulated here. And we have this one more this diagram also. See here. So cold air is blowing downwards, and it is accumulated here. So this is what I call air drainage, and it is also known as katabatic wind. When cold air is blowing downward down the slope, we call it mountain breeze or katabatic wind. And because of this, there will be temperature inversion in the valley area, in the low-lying area. Then here in the box we have two important one very important law is here, and another very important term also here. So we have a law here, Planck's law. Planck's law states that hotter a body, the more energy it will radiate, and the shorter the wavelength of that radiation. It means that hotter objects will radiate more energy, and that also in the form of these short waves. Okay, so that means hotter objects will radiate energy mainly in the form of this short wave. Okay, short wave. And vice versa. If object is very hot, then it will radiate more energy, and that also this shorter wavelengths. In other words, okay, the less hot object will radiate less energy and longer wavelength. And that is why the earth is radiating in the form of long wave. Okay, when we compare this sun and the earth, sun is very much hotter than the earth, and that is why the sun radiates energy, okay, in the form of these short waves, and whereas the earth is not so hot like the sun, and that is why it is radiating, the earth is radiating in the form of long wave, and that is what we call this Planck's law. Okay, and a specific heat, actually this I have explained you in the previous lesson. So this is the energy needed to raise the temperature of 1 gram of substance by 1 degree Celsius. And last time also I explained you that say water warms up and cools down slowly. Why? Because the specific heat of water is higher than the length. That means water requires more heat energy, okay, to warm up. So any question from your side?
Sir.
Okay
No,
then.
sir.
Okay, then let us stop here for today, and this is the end of this chapter. Thank you very much for joining my class. Don't forget to send your names in the WhatsApp group
Thank you, sir.
for the attendance.